Hello students, welcome to the video lecture on DC transient analysis. In this video lecture we are going to discuss about transient and steady state response. So by that we are going to differentiate the terms transient analysis and steady state analysis, followed by first order and second order circuits with respect to DC transient analysis, then source free and forced response. Then we are going to consider one simple case of source-free RL circuit, followed by one example problem to understand source-free RL circuits. Let me introduce the terms transient and steady-state response. As per the equation given here, the complete response of the system or circuit is equal to transient response plus steady-state response, or we can say temporary response plus permanent response. Let me take one simple example to differentiate the transient and steady state response and hence the transient and steady state analysis. Consider the electric fan in our house. If you plot the speed of the fan with respect to time, speed of the fan normally given in rotations per minute, that is RPM. Suppose you switch on your fan at time t is equal to 0. The fan starts run slowly. Pick up the speed. Assume that your fan reaches maximum speed at time t is equal to t1, and it will continue to maintain the same speed till you switch off your fan. Suppose you switch off your fan at time t is equal to t2. Then the fan will not stop immediately. It will take small amount of time to reach its final state or to stop running. Assume that the time is equal to T3. So here the electric fan is our circuit and the input applied to the circuit is 230 volt AC signal, and the complete response of the system or circuit is shown in figure. So as per the equation, complete response is equal to temporary response plus permanent response. So where is the temporary response and permanent response in the figure? So we can say that the initial time period, the circuit takes small amount of time to change from 0 state to the steady state region or steady state value. So this period is called as a transient period or temporary period. So analyzing the circuit during this time interval is called transient analysis. And from T1 to T2, you are seeing steady state response or a permanent response. That is, you have a long time till you switch off the fan, you are seeing the same response in the circuit. So this response is called steady state response. And analyzing the circuit during this period is called steady state analysis. And again from T2 to T3, you are seeing a small amount of time to reach from final state to 0 state. So this interval again comes under transient period, and hence the transient analysis is carried out during this time interval. So your complete response is a combination of a steady state response and transient response on either side. So what is the difference between transient response on the initial stage and transient response on the final stage? So if you remember our contents, we said source-free response and forced response. So this transient response is called forced response. The reason is we are applying force. We are applying voltage. Because of the voltage, there is a transition from initial stage to steady state stage, right? So this is forced transient response, right? But here at time t is equal to t2, switched off your fan. So there is no source, there is no voltage, but still you are seeing some response in the circuit due to the presence of energy storage element. So this time interval or this analysis is called source-free analysis, right? So this entire duration is steady state analysis. So with that introduction, we'll move on to the further topics in the lecture. What is the reason behind the transient response? Why circuits are showing transient response? There are two important reasons. One is the presence of switch in the circuit, and the second one is the presence of energy storage elements in the circuit. Electric circuits are connected to the supply by closing the switch and disconnected from the supply by opening the switch. So this switching operation will change the current and voltage in the device. So which is used to connect the circuit with power supply, at the same time to disconnect the circuit from the power supply. As a result, your circuit is changing from one stage to another stage, and it's taking small amount of time to settle to its new values. So this time interval is, again, it's a temporary period or transient period, and this transient period is due to your switch operation. The second reason is the presence of energy storage elements. If you have energy storage elements in the circuits, such as inductor or capacitors, if you apply input to the circuit, the energy storage elements will not accept the inputs immediately. It may take small amount of time to accept the inputs and store the energy. Similarly, if you disconnect the supply from the circuit, it will not release the energy immediately. Again, it will take small amount of time to release the energy. We know that inductor stores energy in the magnetic field and capacitor stores energy in the electric field. So apart from that, there are two more important characteristics of the inductor and capacitors are: an inductive device will not allow sudden change in current. Similarly, the capacitive device will not allow sudden change in voltage. So these two properties are very, very important in transient analysis. Always you should remember these 2 points before proceeding on transient analysis. Look at the circuits shown in figure. We have a voltage source connected to the single ohm resistor. So initially we are applying 1 volt to the circuit. So because of 1 volt in the circuit, you are seeing 1 ampere current flowing through the circuit. Suddenly, if you change the voltage from 1 volt to 2 volt, then the current also changes from 1 ampere to 2 ampere. But the question is how much time the circuit is taking to change from 1 ampere to 2 ampere. Voltage source change from 1 volt to 2 volt immediately. Does the current change immediately too? Yes. Look at the waveform here. So voltage is changing from 1 volt to 2 volt and current is changing from 1 ampere to 2 ampere. So you are seeing that instantaneously the current also follows your voltage. So this is due to the presence of only resistor in the circuit. So resistor is basically an energy dissipating element. It will not store any energy. So instantaneously it will react to the voltage and current. As a result, we are not seeing any delay in change of its previous value to the new value. Consider the case when resistor and inductor is connected in series. Voltage source change from 1 volt to 2 volt immediately. Does the current change immediately too? So when you apply 1 volt, current flowing through the circuit is equal to 1 ampere. When you apply 2 volt, current flowing through the circuit is 2 ampere. The question is, if voltage is changing instantaneously, does the current change immediately too? So the answer is no. Current will not change immediately because we have a energy storage element inductor. As per the property of the inductor will not accept sudden change in current. It will take small amount of time to change the current value. So we know that the impedance of the inductor is equal to j omega L. So omega is the frequency. For a DC signal, we have omega is equal to 0. So for a DC signal, the impedance is equal to 0. Hence, the inductor will act as a short circuit for a DC signal. So in both cases, inductor will act as a short circuit. If you apply 1 volt, we know that the current flowing through the circuit is equal to 1 ampere. If you change the voltage from 1 volt to 2 volt immediately, current will change to 2 ampere? No, because of presence of inductor in the circuit, it will take small amount of time to change from 1 ampere to 2 ampere. So this time is basically called as a transient period, and the analysis during this interval is our interest in this lecture or in this module. So the remaining period, when your inductor is acting as a complete short circuit, then your current flowing through the circuit become 2 ampere. So this comes under steady state response or steady state analysis. So in this slide, you can see all the possible combinations of circuit analysis. So on the left hand side, you are seeing all the steady state analysis. On the right hand side, you are seeing the combinations of transient analysis. Based on the source you connect to the circuit, we separate as a DC steady state analysis or AC steady state analysis. So this analysis we already covered in the previous modules. Whereas on the right hand side, we have transient analysis. The upper one is we have DC voltage, so it's called as a DC transient analysis. Whereas this one we have AC source, so this is called as a AC transient analysis. So in our syllabus we have only DC transient analysis. In the rest of the lecture we'll be discussing about DC transient analysis. Before moving to DC transient analysis, I want you to remember the voltage and current relationship for resistor, capacitor and inductor. So this is a V and I relationship for RLC during the transient period, and this is the V and I relationship for RLC during the steady state period. Now let's understand what is first order circuits and second order circuits with respect to DC transient analysis. Any circuit with single energy storage element, an arbitrary number of sources and an arbitrary number of resistors is a circuit of order 1. Any voltage or current in such a circuit is a solution of first order differential equation. So we say first order circuit is a circuit that will have first order differential equations for voltage or current. Right? So based on the order of the differential equation we get for the circuit, we are classifying the circuits as either first order equation or second order equations. We are checking the order of the differentiation. If the order of the differentiation is 1, it's going to be a first order circuit. If the order of the differentiation is 2, it's going to be the second order circuit. Okay, so a circuit that contains only sources, resistor and inductor is called RL circuit. A circuit that contains only sources, resistor and capacitor is called RC circuit. RL and RC circuits are called first order circuits because their voltage and currents are described by first order differential equations. So basically any combinations of RL or any combinations of RC are going to produce VI equation in the form of first order differential equation. So the RL and RC circuits is comes under the category of, so the RL and RC circuit comes under the category of first order circuits. Second order circuits, any circuit with single capacitor, single inductor and arbitrary number of sources and arbitrary number of resistors is a circuit of order 2. Any voltage or current in such a circuit is a solution of second order differential equation. So second order circuits, as I mentioned, will have second order or order 2 differential equation for voltage and current equations. So consider the case of resistor, capacitor and inductor connected in series with a voltage source V of t. If you write the KVL equation for the circuit, so KVL around the loop is equal to voltage across a resistor plus voltage across a capacitor plus voltage across an inductor is equal to the applied voltage or input voltage. So we know the V and I relationship for resistor, capacitor and inductor. If you expand the V and I, if you substitute V and I equations into the KVL equation, you will get this equation. So now divide by L and take the derivative so that you can form the differential equation. So look at the differential equation of the circuit. We are seeing that here the order of the differentiation is 1, whereas here the order of the differentiation is 2. So since we have the maximum order of differentiation as 2, the circuit of RLC connected in series is called as a second order circuits. So in summary, we can say the combinations of R and L or R and C produces first order differential equation. So it's a first order systems, whereas the combinations of R, L, C produces second order differential equations. So we have a second order systems. Now let's understand the forced and source free response. Consider the circuit shown in figure. We have a current source and resistor R0 and R and energy storing element L. So please recall the property of the inductor. Inductor stores energy in the magnetic field. Also, it will not allow sudden change in current, right? So we have switch also in the circuit. Suppose if you close the switch and apply the current IS, then current will start flow through the circuit, especially in the inductor and resistor. So we are keeping the switch closed for a long amount of time so that the inductor will act as a short circuit and current will flow through the inductor. So the response in the inductor when you apply the source is called as a forced response, right? So you are applying the force, by that you are seeing some response in the circuit. So that comes under the category of forced response. So in the forced response, a constant current will be flowing through the inductor. When you open the switch, the current flowing through the inductor will not stop immediately. Still there will be a current flow in the inductor and resistor combination. You can very well see that there is no source present in the circuit, but still there is a current flow in the circuit. So this response is called source-free response. Now we understood what is source-free response and forced response. So in this video lecture, we are going to consider only RL circuit. So RL circuit, we said that it is a first order circuit. So again in RL circuit, we have forced response and source-free response. So this video lecture, we are going to deal only with source-free response. So how do you generate the source-free response? To generate source-free response, initially you are applying a source, you are closing the switch. So when you close the switch, current will flow through the inductor and other resistors in the circuit. So when you open the switch at t is equal to 0, then you have only inductor and resistor present in the circuit. There is no source, but still the current will flow through the circuit for a short amount of time. So this is due to the application of source when t less than 0. So we are going to analyze only the combinations of R and L with initial current as I. Okay. So this is a typical diagram of source-free RL circuit. Since there is no source in the circuit, we call it as a source-free RL circuit. But if you ask me, is there any current flow through the circuit? Yes, initially there will be a current flow through the circuit due to the initial current present in the inductor. Right? So consider the series connection of resistor inductor shown in figure. Our goal is to determine the current through the inductor. So the idea is inductor current cannot change instantaneously. So we assume that the inductor current has initial value of I0. So applying KVL around the loop, we have only inductor and resistor. So voltage across the resistor plus voltage across the inductor is equal to 0, right? Since it's a source free circuit, there will not be any voltage present in the circuit, so voltage is equal to 0. But we know that the voltage across the inductor is equal to L into di by dt, and voltage across the resistor is equal to I into R. So substituting the VL and VR values, we have L into di by dt plus R into I is equal to 0, or we can rearrange the equation in the form shown in figure. Again rearranging and taking integration on both sides, and further simplifying this equation by applying the limits of I0 to I of t, and simplifying further by taking natural logarithm of the variables, and finally taking up the powers of e, we will have I of t is equal to I0 into e power minus R t divided by L. So this is the equation for the current I of t flowing through the series, flowing through the R and L combinations, right? So the source free response of RL circuit will have the current I of t, which is equal to I0 into e power minus RT divided by L, where I0 is the initial current in the inductor, and we can define a new constant called time constant for RL circuit as tau is equal to L by R. So substituting tau into this equation, we have current I of t equation in terms of the time constant. So we are defining the additional parameter called a time constant. It's nothing but L by R. Substituting L by R in the equation, we are getting I of t is equal to I0 into e power minus t divided by tau. So for a source free RL circuit, we have seen that current I of t equation is equal to I0 into e power minus RT by L. By applying Ohm's law, we can calculate the voltage across the resistor. So voltage across the resistor is equal to R into I of t, and this is equal to I0 R into e power minus RT divided by L. Also, you can use the same current equation to calculate the power in the resistor. So power in the resistor is nothing but VR of t into I of t. So substituting I of t in the equation, we are getting I0 square into R e power minus 2 into RT divided by L. So similarly, energy absorbed by the resistor or energy stored by the inductor is equal to differentiating power equation with respect to t. We will have L into I di, which is equal to 1 by 2 L into I square of t. So having the knowledge of current I, you should be able to calculate voltage V of t, power and energy absorbed by the resistor or stored in the inductor. Let's consider one simple example to understand source free RL circuit. The 12 volt battery in figure is disconnected at t is equal to 0. Find the inductor current and voltage V for all times. So we have a 12 volt source and switch, resistor 4 ohm and 0.1 Henry and 10 ohms. So as per the question, the switch is disconnected at t is equal to 0. That means when t is less than 0, the switch is closed, right? When t is less than 0, the switch is closed. So when the switch is closed, you are applying 12 volt to the parallel combinations of inductor and resistor in series with 4 ohms. So as a result, after long time after the application of the voltage, your inductor will act as a short circuit. Am I right? So when t is less than 0, your inductor will act as a short circuit since we are applying DC voltage. So now short circuit is in parallel with 10 ohms. So your circuit will, if you calculate the equivalent resistance of the short circuit in parallel with 10 ohms, so this is 0 ohms and this is 10 ohms. The equivalent resistance of this parallel combination is equal to 0. So you can replace this parallel combination by short circuit. So when t is less than 0, you have circuit like 12 volt source, 4 ohms and short circuit. So your circuit will reduce like this. So here we drawn as a short circuit, but basically you have an inductor here. Am I right? So the current I flowing through this short circuit is nothing but the current flowing through the inductor. If you calculate the current flowing through the inductor when t is less than 0, is nothing but 12 by 4, which is 3 amperes. So the current flowing through the inductor is equal to 3 ampere when t is less than 0, right? When t is equal to 0, what is happening? When t is equal to 0, you are opening the switch. If you open the switch, immediately it will not accept the change. So you will have the same current, 3 ampere, will be flowing through the inductor at the time of switching operation. Just after the switch is open circuited, your current flowing through the inductor, still it will be a 3 ampere. When t is greater than 0, the circuit is shown in figure. So you'll have only inductor and resistor in the circuit, whereas the power supply is disconnected. When t is greater than 0, the circuit is shown in figure. We have only inductor and resistor. Am I right? So the current flowing through the inductor is equal to 3 ampere now. This is due to the initial application of voltage in the circuit. So this 3 ampere current will be flowing through the circuit for short amount of time. So now we are going to get the equation for this current. So we derived that the current flowing through the source free RL circuit is equal to I naught e power minus RT by L. So what is I naught? I naught is the initial current. So the initial current we have seen that it's a 3 ampere. So we are substituting I naught is equal to 3, and e power minus, you substitute the value of R and L, so you will get minus 100t. So this is the equation for the current in the source free RL case. Then to calculate the voltage V of t, that is voltage across the inductor, is equal to L into di of t by dt. Substituting the value of I of t in this equation, we will get minus 30 e power minus 100t. I believe you understood the fundamentals of DC transient analysis and one special case of source free RL circuit. So I'll take some more problems in the next video lecture. Thank you.